In this video, we will start discussing the fundamental theorem of calculus. And to get to the statement of this theorem, let's start by taking a look at a graph of some function f of x on some interval a, b, and let's think how we can compute the area under the graph of this function. Now, if you remember the example from the previous video where we discussed the volume of a glass, let's try to use exactly the same idea here. And let's try to imagine what happens as we paint this area left to right. So we are going to take some point x on this interval AB, and then this part of the area up to the point x, let's call it a of x. So now the area will become a function of this variable x on the interval AB. And so what we are going to see is it's actually not that difficult to figure out how fast this area grows as we move this point x. Or in other words, what is the derivative of this function a of x? Now to do that, let's add a small increment delta x to this point x, in which case, of course, the area will also increase slightly by this little strip. And let's call the increment of this area delta A. And we can see that when the increment delta x is very small, or when this strip is very narrow, it's actually very similar to a rectangle. So this increment of the area delta A is approximately equal to the area of this rectangle. And when we look at this rectangle, we can see that its height is exactly equal to the value of this function f of x at this point x. So its area is f of x times delta x. And then if we divide both sides of this equation by delta x, and then let this delta x get smaller and smaller, in the limit when delta x goes to 0, this approximation will get better and better. And in the end, we will get exactly that this derivative of area function a of x is equal to our original function f of x. And of course, if you think about this process of painting this area left to right, this statement is very natural because it just says that the rate of change in this area is exactly equal to the height or the length of your next brush stroke. And then finally, let's rewrite this statement using the terminology and notation of antiderivatives or indefinite integrals that we just introduced. So to say that the derivative of this area function is f of x, it's the same as to say that antiderivative of the function f of x is equal to a of x plus some constant c. And this equation is the statement of this famous fundamental theorem of calculus. So in words, it says that this area function a of x is an antiderivative of our function f of x. Or if you want to put it another way, in order to find the antiderivative of f of x, we can just look at this area under the graph of this function. Now, in this example, we actually cheated a little bit because we looked at the graph of a function which was always positive. So this function was always above the x-axis. But what happens if a function can also take negative values? Well, if f of x is negative, then f of x times delta x will also be negative. And it means that actually, in this case, we are counting the increment of the area with the minus sign. And so, if our function can be both positive and negative on this interval AB, then this area function a of x actually counts the part of the area above x-axis with the plus sign and the part of the area below x-axis with the minus sign. And so if you keep this in mind, everything else in the statement of the fundamental theorem of calculus is the same. And so in the next video, we are going to introduce some more notation and terminology, and using it we will restate the fundamental theorem of calculus in the form which will be easier to use for us in applications.